Hello and namaste. My name is Brandon, and welcome to the next video in my series on basic time series. In this video, we will expand our knowledge of simple exponential smoothing and learn about Holt's double exponential smoothing. And of course, we will do so in a very visual way. So, if you like this video, please like, comment, share, and subscribe. Let's get started. So here is the data we've been using on prior videos. It is Nigeria's GDP per capita from the year 2000 up through the year 2020. We put that data on a chart and it looks like this. We have a very strong trend from the year 2000 all the way up to the year 2015, and then it flattens out a little bit. So using this data and its chart, let's create a forecast using Holt's double exponential smoothing method. Recall that the simple exponential smoothing forecast is a weighted sum of the actual value with a weight of alpha and the forecast value with a weight of 1 minus alpha for that same period. Now, a characteristic of simple exponential smoothing is that when alpha equals 1, it is identical to the naive forecast. So think about it. If alpha equals 1, we are placing all of the weight on the actual value, and then that actual value with all of the weight becomes the forecast for the next period. By definition, that is the naive forecast. However, simple exponential smoothing forecasts lag the actual time series values when the time series has a trend. If the time series has a very strong trend, it is not uncommon for simple exponential smoothing to generate an alpha of 1. Now, the trend makes it difficult for the forecasts to keep up, since there is no account of changes in level from period to period. The Holt DES method adds the ability to account for the trend component of the time series in addition to the level. Holt DES is simple exponential smoothing with an added trend component that helps fix the lag issue. Weights are used to smooth the level and the trend. The Holt smooth value calculation for the level is the exact same calculation as in simple exponential smoothing. The trend component is a weighted difference between the current smooth level and the prior period smooth level. By definition, that is the trend. So if something changes over a period of time, we can see if it went up, went down, or stayed the same. So by definition, that difference of those two levels tells us something about trend. Now we also add in the prior trend, so we can weight that sum between those two things, and that'll become evident here in a second. Finally, the Holt DES forecast for the next period is a sum of those two things. So it is a sum of the smooth level and the smooth trend of the current period. Now, I know this is all a lot of words. It might seem very abstract. However, of course, we will look at this visually. We'll look at some equations and we'll look at a chart, and all this become very concrete very soon. So as promised, let's first build the Holt DES forecast visually by looking at the components that go into each part of building it. Let's start with the end. So we're trying to create a forecast value. Now that forecast value is comprised of two components. It is the current smooth level plus the current smooth trend. So we add those two things together and we get our forecast value. Now each one of those is also comprised of two parts. The current smooth level is comprised of the current actual level in the time series itself, plus the prior period forecast. Now remember, that entire top line there is what we do in simple exponential smoothing. Current actual level plus the prior period forecast, and we weight each one. The bottom component, current smooth trend, is built with the current smooth level minus the prior smooth level. So think about that. We're taking one level minus another level. So that's a change in level. By definition, a change in level is a trend. Then we're adding to that the prior smooth trend from the period before. So visually, this is how Holt DES is put together. And of course, as we see equations and the chart, it will become more mathematically obvious how all this works. First, we have two smoothing factors. We have the level smoothing factor alpha, which is between 0 and 1, and the trend smoothing factor beta, which is between 0 and 1. So here's the current smooth level that we've been talking about. It is written as S sub t equals alpha times y sub t plus the quantity 1 minus alpha times the quantity s sub t minus 1 plus t sub t minus 1. Now on the next few slides we will break all this apart, but for now I'm just showing you what the equations are. The current smooth trend is t sub t equals beta times the quantity s sub t minus s sub t minus 1 plus the quantity 1 minus beta times t sub t minus 1. The forecast for the next period is just those two things added together. So f sub t plus 1 equals s sub t plus t sub t. And then the forecast for the next k periods into the future is very similar, except it's just f sub t plus k equals s sub t plus k times t sub t. All we're doing there is extending the last trend out into the future k number of periods. Now let's break all of this apart. So here's the current smooth level. What we have is alpha, the level smoothing constant between 0 and 1, times the current data value of the time series, which is the current level. Then we add to that 1 minus alpha times the prior period smooth level plus the prior period smoothed trend. Now there is a simplified way to write this equation. It looks like this. All we've done is substitute f sub t where s sub t minus 1 plus t sub t minus 1 is, because by definition that is the next period forecast. So this entire equation at the top is the exact same as simple exponential smoothing, because the way we get f sub t is by adding the smooth level and the smooth trend from the previous period. Now I think when we have situations like this, when our weights are bounded between 0 and 1, is to see what happens when we move them to those extremes. So what happens to these equations when alpha equals 0 or when alpha equals 1? What happens when beta equals 0 or beta equals 1? You can really understand the fundamental ways these things are working like under the hood when we see these extreme examples. So what happens when alpha equals 0? So here's our current smooth level. We substitute 0 in where alpha is. So what happens? Well, we can see that in the first term we have 0 times our current value y sub t. Well, of course, that goes to 0. We go ahead and do that through, and then we end up with s sub t, our current smooth level, is equal to our smooth level from the prior period plus the smooth trend from the prior period. Well, there's another name for that. The name for that is the forecast. So when alpha equals 0, the smooth level is equal to the current forecast. So in the prior period, we added those two things together and created a forecast. Well, when alpha equals 0, that forecast and the smooth level for our current period are the same thing. Now, when we see that in a chart, it will become very obvious sort of how the process works from period to period. But remember, when alpha equals 0, the current smooth level is the same as the current forecast. What about when alpha equals 1? You can probably see what's going to happen here. So we substitute 1 in for alpha, multiply everything through. Now the right side of this equation goes to 0. That's the forecast side, but our current value side stays at 1. So when alpha equals 1, the current smooth level is the same as the current actual level of the data. So the smooth level and the actual level are the same when alpha equals 1. So that was alpha. Now let's look at beta. So the current smooth trend, or t sub t, is equal to beta times the difference between the current smooth level and the prior smooth level, plus 1 minus beta times the previous smoothed trend. Beta is our smoothing constant. We have our current smooth level s sub t, our prior period smooth level s sub t minus 1, then we have 1 minus beta, and then t sub t minus 1, which is our prior period smoothed trend. What happens when beta is 0? So same process. We substitute 0 in for beta. We go ahead and do this math out. So on the left-hand side, our term goes to 0. So everything there on the left goes to 0. Everything on the right stays because it's 1. So we end up with t sub t equals t sub t minus 1. Well, what does that mean? Well, when beta equals 0, the smoothed trend is equal to the trend from last period. It's the same trend that continues forward. So when beta equals 0, we're taking the prior trend and moving that forward in time repeatedly. What about when beta equals 1? Same process, we substitute 1 in for beta. Go ahead and do that math out. This time the right-hand side, the prior period trend, goes to 0, and the left-hand side stays with the 1. So now t sub t equals s sub t minus s sub t minus 1. Well, what does that mean? That means when beta equals 1, the smoothed trend is equal to the current smooth level minus the prior period smooth level. It is a pure one-period difference between those two smooth levels, the current and the prior. We don't factor in the prior smooth trend on the right because it goes to 0. We're looking at just the difference between the two smooth levels on the left. So once we have s sub t and t sub t, the forecast is simple. It's just addition. So the forecast for the next period is s sub t plus t sub t. Our smooth level plus our smooth trend. Add those together, we have our next period forecast. And of course, in the k periods, we just substitute a k before the t sub t, and we carry the last trend forward indefinitely in time. That is how in Holt DES, we would do forecasts, 2, 3, 4 periods in time. We just continue the last trend forward indefinitely. For example, in our Nigeria data, the last year we have is 2020. The GDP per capita in that year was 2396. Now, we want to create a forecast for the year 2021. How do we do that? What do we need? Well, to do that, we have to calculate s sub t, the current smooth level, and t sub t, the current smooth trend. So if we look at the forecast for 2021, it's just f sub t plus 1 equals s sub t plus 1 times t sub t. Of course, we would not write the 1, therefore it's just s sub t plus t sub t. If we want the forecast for 2022, we just take whatever we got for t sub t up there at the top and multiply it by 2. And for 2023, we multiply it by 3. So we're just continuing that t sub t trend, that smooth trend, forward in time. So what happens at the extremes when alpha equals 0 or alpha equals 1, and along with that, beta equals 0 or beta equals 1? Well, when both are 0, the forecasts are all the same level. It's a flat line at the level of y sub 1, our initial value. Likewise, when alpha equals 0, but beta equals 1, we get the same result. The forecasts are all the same level, a flat line at the value of y sub 1. Now they get there in slightly different ways, which we'll see in a second, but the end result is the same. So whenever alpha equals 0, our forecasts are a horizontal flat line that start at our initial level. Now when alpha equals 1 and beta equals 0, that's the same as the naive forecast. There is no trend component to add because we've zeroed it out. So all of the weight goes on the prior period value that gets moved down into the forecast position, and therefore we have the naive forecast when alpha equals 1 and beta equals 0. Now when alpha equals 1 and beta equals 1, the smooth level is the same as the actual level. That's the naive part. And then the trend is the full difference between two smooth levels. So our current and our prior smooth level. We have the full value of alpha, which makes it the naive part. And then we're adding to that the difference between the two smooth levels, and that's our trend. So what we're actually doing is taking the naive forecast and tacking onto it, adding onto it, the trend between those two smooth levels. So what does this look like with our Nigeria data? Well, when both are 0, it looks like this. Again, what I said before. So there's no trend component, there's no level component. The forecast level is a flat line from the first value. So the sort of hot pink color is the actual data, the yellow line is the forecast. Likewise, when alpha equals 0 and beta equals 1, we get the same result, but it's a little bit different. We have the full trend component, but the full trend component is 0. So it's kind of like taking your headphones or something else and turning up the volume to the max on whatever it is, but you don't turn it on. So yes, the volume on my television might be set to 100, but if it's not on, then it doesn't matter. It's 0. There's no volume. Same thing. Therefore, there's no level change. The forecast is flat from this first value. Now when alpha equals 1 and beta equals 0, there is no trend component, beta is 0, but we have the full level component. So the forecast is the same as the naive forecast. And you can see that the yellow line is just the pink line shifted forward one period in time. And then when alpha equals 1 and beta equals 1, we have the full trend component and the full level component. So the forecast is the naive forecast plus the entire 2-period difference between smooth values. That's the trend. We take this current smooth trend, subtract the previous smooth trend. The difference in those two levels indicate a trend. We add that to the naive forecast, and that's what we get when alpha equals 1 and beta equals 1. So here's a chart that will hopefully make all of this stick in your mind a bit easier. So a few notes before we get started. Note that some of the values are rounded. So if you see two numbers that don't quite add up to what it says, they might be off by 1. That's just due to rounding, so the chart doesn't get crazy with a bunch of decimals. Another very important thing to note here is that the alpha and beta values at this stage in this example are not yet optimized. We chose them at random. So we picked a smooth constant of alpha equals 0.8 and a trend smoothing constant of beta equals 0.4. I just picked those numbers because they looked cool. There's no other reason. We could have picked any other two numbers. Could have picked 0.5 and 0.5. Doesn't matter. So right now, this is just based on initial values for this iteration. Now later, we will optimize these numbers using Solver in Excel. But for now, we just pick them and we'll get started. So how do we start this process of Holt DES? Well, first we got to have an initial smooth value and an initial smooth trend. What we do to start this process is that the first smooth level, the first smooth component, is the same as the actual data. So in this case, it's 1,451. So our first smooth level is 1,451. Our first smooth trend is 0 because there is no trend yet. We just put a 0 in that spot. Now, of course, what we do is we use those two numbers to create our first forecast. So our first forecast is just 1451 plus 0. So the first forecast is 1451. Now the next forecast is S sub t plus t sub t, but we don't have those yet. We have to calculate those. So we can see that S sub t is our next smooth level and t sub t is our next smooth trend. But how do we get those? We use all the formulas we saw in the prior slides. So the next forecast looks like this. So let's go through this step by step. So 0.8 is the alpha we chose at the top. So 0.8 there in the blue times y sub t, that's our actual value in our data. That is 1499. So 0.8 times 1499. That's the first half of it. Plus 1 minus alpha, so that's 1 minus 0.8. Multiply that by our prior period smooth value, which is 1451, plus our prior period smooth trend, which in this case was 0. An easier way to say that is it's 1 minus 0.8 times the forecast. Because remember, those are the same thing. So prior period smooth plus prior period trend is the same as current forecast. So the 1451 is the same in both places. We do out all that math. We have a smooth level of 1,489. Now we have to calculate the trend component. So we have 0.4, that's the beta we chose, times 1489. Where does that come from? Well, that is our current period smooth level over on the left-hand side, minus the prior period smooth level. That's 1451. So that's the left side of that equation there, plus 1 minus our beta of 0.4 times the prior period smooth trend. Well, that was 0. So we do that math out, we get 15. So we add together 1,489 plus 15 to get our next period forecast. Now remember, there's some rounding going on here, so it's actually 1504, but in Excel it's 1505. So 1489, 1490 plus 15 is 1505, and that is our next period forecast. Then we just continue this process. So the next period, we have 0.8 times 1686. 1686 comes from the current actual value there in the third column, plus 1 minus 0.8 times 1489. That's our prior period smooth level, plus 15. that's our prior period smooth trend. Another way of saying that is that it's the forecast of 1505. Same thing. Do that math out, and we have a smooth level for period 3 of 1650. Now we need the smooth trend. 0.4 times that 1650, our current smooth level, minus the prior period smooth level of 1489, plus 1 minus beta, so 1 minus 0.4, times the prior period smooth trend of 15. Do that math out, we get 73. So the forecast for the next period, period 4, is 1650 plus 73. So we get 1723. See how this works? Once you have a rhythm for how this works from period to period, it's pretty straightforward. So I've tried to color code everything here so you can see where everything comes from and where it goes and how we figure out the next value and how they're all related together. So we do this whole chart, it looks like this. Of course, I am not going to go through all of these. You can pause and look at it on your own, but it's the exact same process carried forward. So our data ended in the year 2020. Nigeria's GDP per capita for that year was 2396. Now we want to find the forecast value that's over on the right where the question marks are. A few things are in this calculation. 2499 is the prior period smooth level, so it would actually be in the row above. Same thing for the negative 24. It is the prior period smooth trend that would also be present in the row above. But we carry those down and we do the math out and we get a smooth level of 2412 and a smooth trend of negative 49. Mathematically, it looks like this. We have 0.8 times 2396, that's our current actual level there in GDP per capita, plus 1 minus alpha times the quantity of 2499, our prior period smooth level, plus our prior period smooth trend, which was negative, so it's plus negative 24, and we have a value of S sub t of 2412. So T sub t, our smooth trend, 0.4 times 2412, that is our current period smooth level. You can see that there in the fourth column, minus the prior period smooth level of 2499, plus 1 minus beta times negative 24, which is our prior period smooth trend. Do that math out, and we have negative 49. So we add those together, which is actually subtraction in this case, and we have a forecast for the year 2021 of 2363. So we put that forecast in our chart, and we can see it there below the forecast for 2020. So, based off this data, our forecast for Nigeria's GDP per capita for the year 2021 is $2,363. We put that on a chart and it looks like this. So our data point falls right about there, which makes sense. It seems like that's pretty close to the ballpark of where we'd expect it to be. But remember, this is not optimized. We haven't optimized our alpha and beta yet. But that looks pretty good for just picking alpha and beta at random. Now, of course, we don't want to leave alpha and beta to random chance, just hoping we pick the best values. We want to optimize them. Luckily, we can do so with Excel's solver. So the explanation is, what weight values for alpha and beta minimize the forecast error? So it could be anywhere within this matrix. Alpha is on a continuum from 0 to 1. Beta is on a continuum from 0 to 1. It could be any value in between those and including those. It could be any or none of these highlighted areas in this chart. But somewhere in this square, there's a combination of values for alpha and beta that minimize the forecast error, and Solver can help us find it. So here we are in Excel, and I just wanted to briefly show you how I use Solver to find the optimal values for alpha and beta. So everything in this chart is what we've done before. We can see the formulas for everything. So here's a forecast formula. It's just the sum of the smooth and trend from the prior period. If we pick a smooth value here, we can see everything that goes into that. Again, this is just the Excel version of that mathematics. I'm not going to go into that in this video, but I might make a separate video doing it step by step. But rest assured that everything here is correct and the same thing we saw in the PowerPoint version of this video. We can also confirm this by looking at the forecast for the next period. So 2363 was the same forecast we got when we did it by hand in the PowerPoint. So here we have an alpha of 0.8 and a beta of 0.4. Remember, we chose those at random. We just like those numbers and put them in there. Of course, they have to be between 0 and 1. Now, what I'm going to show you how to do is pick values for alpha and beta that minimize the mean square error, or the MSE. Remember, that's the point here. We're trying to minimize the error. Now, the chart on the right is live, so it is connected to the data. So if I typed in 0.5 for alpha and 0.5 for beta, everything changes. It's all live, it's all connected. So we can see that if I change it to 0.5 and 0.5, the mean square error went up to 7657. If I put them back, it's 5029. It's much less. But we want that to be as small as possible. Let's use Solver to do that. So I'm going to go up to Data, and again, I'm on a PC. I'm going to go to Solver, and it's going to ask me a few things. I have some values in here from before because it does remember those. So what I'll probably do is just delete this for now, and delete that, and delete this. We'll start fresh. Okay, what is Solver wanting from us? First, it wants to know what we are trying to do. Are we trying to maximize a value, minimize a value, or set a certain cell to a specific value? In this case, we're trying to minimize the mean square error. So min, then we'll select our mean square error cell here by changing what? Well, we want to change these two cells right here. Let's select those two, and we have D25 and D26. Subject to what constraints? Well, remember that alpha and beta have to be between 0 and 1. So we're going to add a constraint. We'll select those two cells again at the same time. They have to be less than or equal to 1. We'll click Add. We'll close this. And now we have the fact that these two values cannot be greater than 1. We will also select this Make Unconstrained Variables Non-Negative. That makes sure they are not negative. So we know that they're going to be not negative and less than or equal to 1, which is the constraints we have to have for this type of model. Now in this case, we have to select GRG nonlinear because of the type of optimization we are doing. If you selected simplex LP, you'd probably get an error because we're kind of doing a grid search here between these two variables. So GRG nonlinear is the best to choose. So we have minimize our mean square error by changing the cells alpha and beta over here, subject to the constraints that these two variables have to be between 0 and 1. We'll go ahead and click Solve. It says it found a solution. We say OK. And now we have an alpha of 1 and a beta of 0.653 approximately. Now our mean square error is at its lowest of 3,896. Now I can change this back. So remember 3896. If I go 0.8, 0.4, now we have an MSC of 5029. I can go back up to Solver. So 5029, Data, Solver, it remembers everything. Run it again. So 5029 to 3896. So these are the values of alpha and beta where a mean square error is at its lowest. And we can see the chart over here on the right that we saw in the PowerPoint part of the video. And because all of this is connected in one sheet, we get all of our other measures as well. So we get our root mean square error, we get our MAPE, SMAPE, and maze. So let's go back to the PowerPoint and finish this out. So using Solver, we found these two values. The optimal alpha is 1 and the optimal beta is 0.653. So how do we interpret that? Here is the explanation. The forecast is the smooth component plus the trend component. At alpha equals 1, the smooth component of the next period forecast is the same as the actual value for the current time period. That's the naive forecast. Now with beta equals 0.653, the trend component is about 65% of the difference between this period's smooth value and last period's smooth value. So for this data, in this case, what we're actually doing is taking the naive forecast, because alpha equals 1, and then adding to it a trend component. That trend component is about 65% of the difference between this period's smooth and last period's smooth. So here is the optimized calculation using those values from Solver. Substitute everything in, we end up with a forecast value of 2,320. Put that into our chart, and it's there in the lower right. Now let's compare that to our non-optimized forecast. Let's compare non-optimized and optimized on our chart. So the first value here in the pink is our optimized value of $2,320. The gray dot is the non-optimized value of $2,363. There is not much difference between those two, but there is a difference. And remember, even though the difference is not a lot, that's due to chance because we picked alpha and beta completely at random. If we picked worse numbers for alpha and beta, the difference between these two would be greater. So here's a chart of our actual data there in the blue, and then the Holt Double Exponential Smoothing forecast there in the hot pink. You can see it follows very closely. So up until now in our video series, the quadratic trend projection was the best. And here are those errors in blue. Now here are the Holt errors in the hot pink. Notice that there are some places where the Holt errors are larger, but if you look through the middle of the data series, the Holt errors are extremely small, almost invisible. So you can see that it appears that the Holt is slightly better, but it's close. We won't really know until we do the forecast accuracy measures. But here is the best up till now compared to the Holt DES we did in this video. So here we have all of the errors for all of the forecast methods we have learned up to this point. We have the naive forecast, the 3-period simple, 3-period weighted, exponential moving average, linear trend projection, quadratic trend projection, and then the Holt DES there in the hot pink. We can see the Holt DES errors are very, very small compared to especially the first 5 methods. The quadratic trend projection is pretty close to the Holt DES. It is there in the darker blue, and the Holt DES is there in the hot pink. So you can tell just by looking at the errors that the Holt DES method will be very similar to the quadratic method in terms of their accuracy. And those two together are much better than the other 5 methods. But we won't really know until we compute the metrics for the forecast accuracy. So we can see that in the first column, the mean absolute error, that the Holt DES with alpha of 1 and beta of about 0.65 has an MAE of $46.99. That is by far the best. It is close to the quadratic trend, but it's even better than the quadratic trend. Same holds true for the root mean square error. So Holt has a value of $62.42. Quadratic had a value of $66.29. Again, much better than everything else, and those are pretty close together. The mean absolute percentage error, or the MAPE, is 2.18%. Again, that is the best. The SMAPE is 2.11%. Again, the best, but close to quadratic. And finally, we have a MAISE of 0.614. Remember, the MAISE is a comparison to the naive forecast. That's why the naive forecast has a MAISE of 1. So for Holt, a MAISE of 0.614 means 2 things. It means it is the best of all these methods, and it means it is far better than the naive forecast, because any value with a MAISE under 1 is better. Any value with a MAISE over 1 is worse than the naive forecast. So using Holt Double Exponential Smoothing and Solver to find the optimal alpha and beta, we were able to wring out a lot of error in this forecast accuracy matrix. Okay, that wraps up this very comprehensive video on the Holt Double Exponential Smoothing method, taking a very visual approach. If you've hung around this far, I really appreciate it. I know this was a longer video, but once these methods become more complicated, it's really important to understand how they are put together. So I wanted to show you visually with the equations and with the chart, and of course using the solver aspect, how all of this fits together. Not only that, but how it all fits with the other methods that we've learned. Now, especially with longer videos like this one, I deeply appreciate the time you put in to watch. So I hope you found it helpful, enjoyable, and insightful, and I look forward to seeing you again in the next video. Take care and bye-bye.